Welcome to our beam vibration presentation. Enjoy!
The three main objectives for this experiment were to obtain results theoretically, then verify results experimentally, and then finally compare experimental and analytical results.
The beam properties were obtained at the Sound and Vibrations Lab in 1017 Furnace Hall.
Here is the theoretical frequency response obtained using MATLAB. The three peaks shown represent the three natural frequencies.
For a uniform cantilever beam clamped at x equals 0, the differential equation is depicted in equation 1 as well as its boundary conditions in equations 2 and 3. Previous equations lead to equations 4 and 5, which then yield the characteristic beam equation shown in 6. From this characteristic equation, the three eigenvalues can be found. Plugging these into equation 7, the natural frequencies can be found.
The three beam modes were plotted in MATLAB and can be seen in the graph shown. One static node can be observed in the second mode, and two static nodes can be observed in the third mode. ANSYS was used to create all the modes shown here. First mode, the second mode shown here, the third mode here, and then the fourth mode, which is actually the vibration of the plate. The experimental setup contains two main parts. The first part involves generating a sine signal with the signal analyzer. The signal varies from 0 Hz to 350 Hz. This signal is transmitted to the amplifier and to the computer. The amplifier controls the shaker. The accelerometer monitors the displacement at the free end of the beam. This displacement is sent back to the analyzer to obtain the frequency response. The second part is to take each natural frequency and send a constant signal to the beam. The scanning head then uses a mesh of 29 by 7 points to obtain the displacement values at each node. The vibrometer checks to see if the node is optimal. If not, it rescans. Then the computer creates an animation of the vibration mode.
The sine sweep depicted here is the frequency response of the beam. The first two modes can be captured by the camera, as seen here. The third mode cannot be captured due to the high frequency.
The vibrometer created these animations. The first mode here, the second mode, the third mode follows, and finally again the fourth mode is the vibration of the plate. Both frequency responses match each other well. It is important to note that during the experiment, a fourth mode was found. This fourth mode is the frequency at which the beam vibrates like it was a thin plate.
The exact solution was found using the Euler-Bernoulli beam equations. A second analytical estimate was obtained by using a FEM approach. These two methods have minimal error and therefore are accurate. The Euler-Bernoulli method was then compared to the experimental results. The first two modes are pretty accurate. The third mode differs by about 5%, which is an acceptable experimental error. The simulated mode shape from ANSYS corresponds to the vibrometer mode shape well.